Yeah, thank you very much. Well, it's a great honor for me to come back to here to give this talk. 10 years has passed, and I think the IPMU has accomplished a great deal. And I'm very happy to give this talk. The talk will be in general relativity. I started to work on this I started work on general relativity about 40 years ago in 1977, where my friend Rick Stern and I first proved the positive mass conjecture in that year. Since then, we made a lot of progress, I think, with many mathematicians. But on the other hand, it's not in the same scale as what physicists would like to see. The only difference is that we do prove things, that whatever we did, we are 100% sure that it's right. But as a result, it's a much slower progress than what we like. But the field is still moving very rapidly from our point of view, and it's also tough. The reason is that this equation, which you're all familiar with, the Einstein equation, is rather nonlinear. And the left-hand side involves second-order differentiation of the metric tensor, which is complicated because of the crystallable symbol term. And this has been very difficult for geometers to work on it. We do need people from partial differential equations, ideas from many different subjects to come together to help out. But geometry and physics is still the major background that we need to deal with. So most of these are familiar to you, so I would not say too much. So we all know that this is a great achievement by Einstein. But Einstein thought that the equation, in some of his writing, said that the equation determined gravity completely. But this, of course, is not true because we do not know the initial condition for the field equation, when we also have difficulty to identify the boundary condition for this Einstein equation. It's a second-order hyperbolic system, and there are two major things which we still do not understand very well: the initial condition and also the boundary condition. And make it worse is the gauge problem that we have to deal with constantly. And half the problem of Einstein equation comes from understand how to deal with gauge. Now, there are many important problems for classical relativity which are not solved. The major thing are the structure of the singularity that comes up. Well, of course, we know black holes appear in the classical solutions, Schwarzschild and Kerr solutions. And based on that, Penrose proposed the very famous question of cosmic censorship, where he claimed that for genetic spacetime, every singularity is hidden behind some membrane similar to black hole. So this is a very tentative and yet deep questions for people working in GR. The reason it's difficult is that many important concepts in these nonlinear equations are not well understood. It's only understood in a very weak field limit. In the case of the whole global dynamical problem, it was solved about 20 years ago by Crisaldolo and Kleiman, which means a small perturbation of the Minkowski space-time. And this was not easy already. They wrote about 300 pages book on that. It could be simplified, but it's still not trivial. So even in this simple case, we still have difficulty to understand it transparently. Now, in order to understand many of these questions, including singularity and this global dynamical system, it comes from some difficulty comes from that many important physical quantities that were understood in Newtonian mechanics is not well understood in GR. This is largely due to the problem of gauge choice. but also because of the nonlinear nature. Even a simple case of a mass, the concept of mass, is not trivial. Einstein himself succeeded to define the total mass for an isolated physical system, which was made precise by the famous work of ADM. And this was already a non-trivial problem, because what does that mean to be an isolated physical system in terms of mathematics? Even now, I think it's not 100% understood. We assume the metric decays in a suitable way to the Minkowski space-time, but how fast it decays and all that is not so well understood, actually. Anyway, as I mentioned, I've actually started to solve the problem that Einstein liked to know, that is positive in order for the system to be physically stable. The complete solution was finished by Rick Shen and myself in 1979. So that was already quite non-trivial. Now, we like to, ever since then, I was motivated to understand more physical systems and more physical quantities that appear in GR. As it's well known, we cannot define mass density of gravity in GR. The reason is that we can always choose a coordinate system where the first order differentiation of the metric is equal to 0. And therefore, by equivalence principle, the mass density has to be equal to 0. As a result, we cannot define mass density. But nevertheless, it's still important and desirable to measure the total mass in a space-like region bounded by a closed surface. Well, one important reason, for example, is to understand a binding mass for two black holes interacting. We've got to understand what is the mass of one single black hole in a two black hole system. And without a suitable definition, we could not say much about it. So we need to get some understanding what gravity means for a space-like two-dimensional surface. The gravity that is enclosed by such a surface. Well, so we propose that the mass due to gravity enclosed by this space-like region should be computable from the intrinsic and the extrinsic geometry of the surface itself only. Not the region inside, but only the surface itself. So this builds in some conservation of mass inside there, because the surface can bound different space-like hypersurface. So it's an important question, and this was actually, I learned it from Roger Penrose back in 1979, when we had a special year in the Institute for Advanced Study. And that was, in fact, a very interesting special year where several famous relativities come. And Roger Penrose wanted to know what is a quasi-local mass, namely this definition, this question I just asked. What is the definition of such a thing? And Roger Penrose lists it as the first major problem in his open problems that I asked him to compile. So he put down about 10 problems. This is the first one he wanted to know. And this problem was worked on by many people, including Hawking, Penrose, Hawking, Horowitz, Brown, York, Barnett, and many, many others. And well, actually, more than 15 years ago, I was interested in how to formulate a criteria for existence of a black hole that Kip Thorne called Hopf conjecture. The statement says that if the quasi-local mass of a closed surface is greater than a certain multiple of the diameter of the surface, then the closed surface will collapse to a black hole. So Kip Thorne actually formulated such a problem in a much more physical way, and as a result, there's no precise definition whatsoever. So he just called it mass of a closed surface. And so we need to know what a quasi-local mass is in order to even formulate this conjecture. And according to Kip Thorne, it is a black hole collapse if and only if this inequality holds. Actually, Rick Stern and I managed to prove a special case of this conjecture about 30 years ago, without knowing Kip Thorne's paper, actually. But in any case, we didn't prove the general case because we don't know what is the definition of quasi-local mass. So that's one motivation. I need to know what quasi-local mass means. So I thought about it, and as a mathematician, I want to formulate what is needed. So we want to know what kind of properties that a definition of mass is supposed to satisfy. So I put down several criteria, and there's some more later. But the first one is it should be non-negative. The mass that is enclosed by a surface, the mass due to gravity, and it should be trivial for any closed surface in the trivial Minkowski space-time. This first statement looks easy to say for any physicist, but it's actually one of the most difficult things to do. You just imagine, given you a closed surface in any space-time, which is four-dimensional topology, you want to associate a number so that it's non-negative and in fact non-zero, and yet it's trivial for all closed surfaces in the flat space-time, where there are plenty of them. And this is difficult to hold, and it was a long struggle for us to find such a definition. And then it should converge to the standard ADM mass, which is actually went back to the definition given by Einstein himself. If the spheres will approach the spatial infinity of the isolated physical system. And number 3 is that you should converge to a boundary mass when the sphere diverges to a cut and now infinity. So these are 3 very important assumptions that we have to make on the definitions, because these are obvious, has to be true, otherwise it doesn't make sense. Number 4 is that it should be equivalent to the standard Kolmar mass in a stationary space-time. This is assuming that we have non-trivial action, like sphere, SU2 action on the space-time, and then there's a well-defined Kolmar mass, which comes out from Noether's theorem. Now, it turns out this is not exactly true, but I say it's equivalent. So what we are going to define, the mass would not be exactly equal to the Kolmar mass, but it would be equivalent in the sense is that it's less than equal to 2 times the Kolmar mass and bigger than equal to half of the Kolmar mass. So in all practical purpose, it is the same. So these are the 4 criteria I want to put down to make sure the mass will satisfy. Well, so we have to motivate the definition by the Hamiltonian formulation or the Lagrangian formulation of GR using the Hilbert action. For a closed surface enclose a space-like region, D. Now, we are trying to define something on S. So we make assumption that you enclose a space-like region, D. And these are important, actually. It sounds innocent, but given an abstract surface, you can define something. But it does not satisfy the properties that we want unless it encloses a space-like region, D, in a space-time which satisfies the local energy condition. So this actually is an assumption by itself. A surface should enclose a region, D, which satisfies, which is embeddable in a space-time satisfied energy condition. Then the Lagrangian formulation using the standard Hamiltonian mechanics, we found this quantity, which can be looked at as the mass, the energy of the surface. But here involve several things. Suppose I take a future timeline unit vector field in the space-time, W, and I decompose it into 2 parts. One is in the normal part with n there, which corresponding to the Labs function. And then n mu is a tangential part of the vector field. Then we found out this quantity n times K2. K2 is the mean curvature surface, of the surface, and P mu nu is the second fundamental form of the three-dimensional manifold D. So this is the quantity that you can find, which is well motivated by Hamiltonian mechanics associated to the Hilbert action. Now here is a problem here. There are several things depending on choice of gauge. One thing is D, the choice of D. D could be different depending how you choose it. And N and N mu are choice of gauge of the observer. W mu corresponding to observer in space-time. It decomposes into two parts. So N and N mu needs to be chosen. Well, in time-symmetric case, which Brown and York work on, assuming P mu nu equals 0, he take N equal 1 and N nu equals 0 in that formulation. And then he wrote down a surface and wrote down the quantity that I just wrote down earlier. But this would depend on the choice of gauge, because N equal 1 and N mu equals 0 is kind of ad hoc. And it certainly depends on the choice, on the boundary. Nonetheless, when I told my friends in Hong Kong, C and Tam, they managed to prove the positivity of this quantity, assuming N equal 1 and N nu equals 0 in the time-symmetric case. So after this, we feel somewhat confident that this approach would work. And Melissa Liu in Columbia now, we refined the definition to make it to be gauge independent. So we come up with this quantity that I wrote down here. And this quantity is good, and it is non-negative. In fact, we proved it in a very general situation, including non-time symmetric case. The proof is very non-trivial, actually. But it turns out it is very good in all situations. It demonstrates the four criteria that I wrote down earlier, that it all holds for this definition. Unfortunately, it's too positive. Namely, it's not trivial for a surface in Minkowski space-time. So this quantity is not quite the standard mass we'd like to see, because it's not 0 for an empty space-time. So finally, about 9 years ago, it was 8 years ago, Muda Wang and I achieved a definition that satisfies those criteria. And this depends on many works that I mentioned here, which I won't go into detail because the proof actually is rather involved, very complicated. So let me tell you what the definition is. The definition is defined in the following way. Suppose I have a surface S, a closed surface, which we assume topologically S2. Topologically, it has genius equals 0. And we know that it can be embedded isometrically into Minkowski space-time. This is an important fact, not true in high dimension or for other surfaces with high genius. And for topological surface, we can always isometric into Minkowski space-time. So we do that. The Minkowski space-time would be a reference frame, so to speak, to the definition we are going to use. It will be fixed. And we fix a future timeline vector W in this Minkowski space-time. This will be a constant vector. And the observer is traveling in Minkowski space-time in the future timeline direction. We then look at this surface. So let me give you the picture. The left-hand side is the reference frame. I isometric embed the surface into Minkowski space-time. And the right-hand side is the actual surface that's sitting in space-time. And the left-hand side, we have an observer, W nu, traveling in constant speed. So what he will do, he look at this surface coming from the surface sitting in space-time. He look at the expansion or the contraction of photons sitting at this surface. That will be h0 dot W on the left-hand side. So H0 is a mean curvature vector of the surface sitting in Minkowski spacetime. H0 dot W is the area contraction or expansion when the observer is traveling on W. That's exactly what you will see. So what we do is that we equate it with H dot W bar. H is the mean curvature vector of the surface in spacetime. W bar was not chosen before. Now I define a W bar to be a 4 vector in spacetime, satisfy this equation. So what I'm requiring is that I choose a gauge in spacetime so that the contraction or expansion of photon bouncing on the surface is the same as what you see in the reference frame. So we choose a reference, not only isometric embed into there, but also the timeline expansion or contraction of the area is the same. So this is a very important choice. And this is the only part which we don't think in terms of physics, but yes, in a way it is. We kind of cooked up this one from the necessity of geometry. It's motivated by but deeper geometric reason that we choose this. Anyway, so what do? We have this quantity which I mentioned earlier. Previously, I said I do not know what n is and n mu is. Now I know what n and n mu is in both cases. One in the Minkowski spacetime, one in the original spacetime. Now in the Minkowski spacetime, we have this same quantity k0 and p0. It turns out this quantity could be understood very, very nicely. Well, why is it nicely? So this quantity turns out to be the total mean curvature of a new surface called S hat, which is obtained by the projection of S into the orthogonal complement of the observer, W mu. So let me give you the picture. So I have S sitting in Minkowski spacetime. It's not lying in any hyperplane. I project it into a hyperplane, which is orthogonal to the observer, W nu. So you get a new surface, which I call S hat, sitting in R3. And I look at the total mean curvature of this surface in R3. It turns out to be exactly equal to this quantity, which looks funny at the beginning. So this is a very important observation, that this quantity is actually equal to total mean curvature of the surface. So this takes a non-trivial work to work out. Some special case was worked out by Gibbons. Okay, now we have this property. Now the important thing is that we know how to choose a gauge. And also we know some properties of this, this quantity. Then what we do? We take the two quantities. One is in the space-time with a k bar and p bar there. I subtract out the reference. So I subtract out the one that isometric embed into R3, comma 1, and I divide this with E. So E would be the difference. One is subtracted out by the background, and the other one is the actual one obtained from the Hamiltonian mechanics. And I divide this to be H pi E. Now, very importantly, and this is where the most difficult part, is to prove this quantity, in fact, is always non-negative. So this rather complicated procedure is actually difficult to imagine this should be non-negative, if not because the last 20 or 30 years work that we have been putting in this kind of analysis to prove that this is actually non-negative. So we know this is always non-negative. The non-negativity comes out from the fact that the surface S bounds a D, a three-dimensional space-time hypersurface, which satisfies the local energy condition. So the local energy condition of space-time is used here to prove E is non-negative. Okay? The local energy condition is used, otherwise it cannot be true. And we define the quasi-local mass to be infimum of E, where the infimum is taken among all possible isometric embedding into R3, 1. So this gives rise to a definition of thing. It turns out the optimal embedding that achieves the quasi-local mass can be calculated. It looks like this, where tau is unknown, it satisfies fourth-order nonlinear elliptic equation. And in general, it should be unique. We could prove it in most cases, not always though. Now, this actually embedding is very useful, this tau. So we have an isometric embedding which is governed by nonlinear elliptic equation. So we can calculate the quasi-local mass using this equation. This equation can be solved without much problem on a computer. So in summary, given a closed space-like two surface, we have obtained such a quantity which satisfies all the problems that we want. When we approach a point by taking small spheres along null geodesics, it will recover the energy momentum tensor of matter density if the matter is there. Otherwise, we recover Bell-Robinson tensor if the space-time is vacuum. So this gives rise to a very nice property of in the limit when the sphere goes to 0. And then we look at the things besides quasi-local mass and to other quantities like angular momentum. It was in the title. So given an isometric embedding and an element of the Lie algebra of the Lorentzian group, we can define quasi-local angular momentum and quasi-local center of mass, corresponding to pairing this element with rotation Killing fields and boost Killing fields, respectively. Now, this is a rather interesting quantity, which I think it should have some physical meaning, which we don't know yet. Given the isometric embedding, the optimal isometric embedding, we have the quantity tau, which I define here low. And it's kind of like the density, energy density, and I have a matter density here. The optimal embedding equation takes a rather simple form. It says divergence J equals 0. This is corresponding to the fourth-order nonlinear equation. Now, the interesting thing is that all the quasi-local conserved quantity turns out can be defined by this formula. So this formula says that given a Killing field in the reference frame, we plug in this quantity, where low is the density that I just defined, and J is the momentum that I define in terms of the isometric embedding. This quantity turns out to be good and defines the quasi-local angular momentum if I use K to corresponding to rotation vector field, and define the center mass in case I use this boost field. And this has many important properties that satisfy in a very nice way. First of all, it vanishes for Minkowski spacetime, which I said is actually a non-trivial statement. And they obey classical transformation law under the action of the Lorentzian group. Now, this is a very non-trivial statement to check, actually, these properties that I just mentioned here. Number two is this angular momentum are always finite. Now, this sounds like a trivial fact, but it's actually non-trivial. If you remember, when you define the rotation vector field, there xi timing there, and it's divergent, just brute force integration, you have to see how the cancellation comes. And this cancellation actually has bothered people for a long, long time. And our quasi-local mass actually resolved many of these puzzles. And then, number three, under the vacuum Einstein-Soroszin initial data set, the center of mass actually obeys a very simple dynamical formula. It's just P equal to mv. Now, this seems to be interesting, well, not interesting for people working in classical Newtonian mechanics, but you have to understand these things are defined quite independently. P is the ADM energy momentum forward vector, and C is defined in the way that I define it, center of mass. D over dt comes from evolution of the Einstein equation. The evolution-Einstein equation is not used in any of this definition. But it comes out to satisfy this law, which is rather amazing to me that it holds. Actually, when we calculate it, at the beginning, we make some mistake, but it turns out to be right. So the angular momentum has been actually, even with total angular momentum, has been a difficult thing, but we were out that. because, as I said, the angular momentum is easily divergent, and it turns out to be phi using the definition correctly. Now, I don't have time to go because time is getting short. But anyway, we have quasi-local quantity where we have energy, linear momentum, angular momentum, and center mass. And we prove finiteness theorem and invariance theorem for all these things. And these can all be generalized to anti-de Sitter space without any problem. De Sitter space is a little bit different because de Sitter space you could close up, and we could, if the reference frame is only half the de Sitter space, is phi, but not the whole thing, which is completely reasonable. And etc. This equation I just mentioned to you, the evolution. And now there's another thing that would be interesting. If we perturb the Schwarzschild solution, and we get a quasi-local mass, get a quantity of order 1 over d squared. In other words, if I measure a small sphere far away from the quantity, from the black hole, it could give rise to some energy which we can use to measure gravitational radiation. And it turns out 1 over d squared is too small. But on the other hand, we can use some tricks in geometry to measure the flux. So in other words, I take a closed loop, say on the Earth, near the Earth, to measure the gravitational flux coming from a black hole far, far away. And by doing that, I can get some quantity of order 1 over d. It's kind of like measuring the mass aspect of the Brownian mass. And this is very interesting to me because I can use this geometry to measure gravitational radiation, different from what people have been using now. This loop can be changed in geometry and should get different quantities that we can measure from far away. So these are being explored, and I think it will be interesting hopefully for experiment. Anyway, I stop here.